Hi folks, and welcome to Open Analysis Live. So today we're going to do another one of our deep dive reverse engineering tutorials, and we're going to talk about how to decrypt encrypted strings in malware. So we're going to talk about, first of all, how to identify if there are encrypted strings, then how to identify the encryption algorithm and reverse engineer it, and then lastly we're going to talk about how to implement that in IDA Python, scripting in IDA, so that you can automatically decrypt the strings in the binary. Now this is, I think, the fourth video we've done using REvil, the REvil ransomware, as our sample, and I'll link to the previous videos below. You guys can go and catch up on the other tutorials we've done with this sample. So we've actually showed you guys how to unpack it, how to resolve the dynamic imports and label them in IDA, and then in this video we're going to be talking about how to decrypt the strings. And I would say in general, if you're doing malware analysis, being able to unpack, resolve the imports if they're dynamic, and decrypt strings are the three basic things that you need to do before you can actually start analyzing the malware. So I would say if you put these three tutorials together, you're probably going to have a pretty good base to start actually reverse engineering the binary and figuring out what it does. Now before we jump into it, a quick word from our sponsors, which is us.
UnpackMe, a malware unpacking service from Open Analysis. Expose the malware before it exposes you.
Don't worry, we didn't pay for that commercial. But all jokes aside, head over to UnpackMe if you guys want to do some automated malware unpacking. It's a free service. Sean and I maintain it, and hopefully you guys find it useful when you're analyzing malware. We try to basically unpack all the samples that are out there so that you guys can get the payloads quicker and start your reverse engineering quicker. All right, so with that, let's dive into our REvil sample here. I have it loaded up in a shiny new IDA 7. I think Santa dropped a new version of IDA in my stocking this year. So we're starting this year fresh with IDA 7 and the IDA 7 API. So here I have REvil loaded up, and if you guys remember from our last video, we basically went through and we identified that there was a import address table building function here where they basically dynamically resolved all of these imports. And if we see here, we went through and we used an IDA script to actually label all of the imports here, which are all now labeled in our binary. So that's where we left off in the last tutorial. Again, I'll link that video below if you guys haven't watched it. We show you guys basically how to identify these imports and script it up so you can label your IDB. And so we're starting with a nicely labeled IDB here. And one of the tricks that one of my coworkers has been using for a while, and I want to show it to you, that's kind of cool. If you guys have the Hexrays decompiler, so this shows you the pseudocode, there's this really nice sort of window view that Guidra uses, and I find it really useful in IDA. So I'll just show you guys quickly how to do that before we dive into reverse engineering here. So what you need to do is F5 obviously to get your pseudocode here, and then you can grab the window and sort of drag it down. You see this like little settings panel here. So you set it as a split panel, and then you sort of move this over. And what you can do is you can right click on the pseudocode, synchronize with your IDA view, and now anywhere you click in the disassembly, you can actually see it in the pseudocode. So it's actually kind of helpful if you're trying to figure out how the disassembly matches up with the pseudocode here. So now that we have this sort of set up, we have our disassembly here and our decompiled version here. Let's go back and I'll show you how I identified that there were some encrypted strings here. And I'm going to switch this from the graph view into the text view here because I like that better. So this function, if we just do an xref here and find out where it came from. So here's where we built our import address table in the last video. And you can see the next call down here is an API that we resolved, and then the next call down here is this function. So I just started reverse engineering. I took a look at this function here, and I can see that there's a call to create mutexw. And if we pull up the documentation from MSDN for create mutexw, you can see that this third parameter is the mutex name, and that's actually supposed to be a pointer to a wide string. And so if we look here in our IDB, we can see that this is going to be a wide string, basically, right? The problem is that it's not a wide string. It's a variable, and it's a variable that is passed by reference to this function right here. And there's a bunch of other stuff being passed to this function. So we see a pointer to somewhere in memory, and we can kind of see what this looks like here in memory. It looks like a big array of garbage. And then there's a couple values passed to this function, and then this what is going to eventually be a wide string is passed by reference. So if we take a look at this function, we can see that it's a wrapper around another function here. And if we take a look at this function, you can pretty much immediately see what's going on here. And if you didn't spot what I spotted, I will link our video to reverse engineering RC4 encryption in the video below. This pattern right here is identical to what we showed in that video, and pretty much identical to every RC4 encryption algorithm that you're going to see out there. So this is RC4, and that's obviously there's RC4 encryption going on here. And if they're passing in a string by reference and then using it in a function, I'm pretty sure that that's going to be some string decryption using RC4. So this literally took like, a minute to figure out that there's encrypted strings and the algorithm that they're encrypted with.
Check out the big brain on Brad.
But again, that's only because I already have memorized this pattern for RC4 encryption. So just to walk through it a little bit slower, what we can see here is we can see there's a bunch of different variables here that are being passed in. And if we just pop back, what I want to do is I want to follow the final argument here is the wide string by value or by reference. So we can see here that that is the final thing here. So that's the final variable here. So we'll name it argwstr, and we'll pop in here, and we can see again it's passed by reference, and it is a byte string. So that again kind of makes sense that they would be returning a byte string in this variable. So it's a pointer to a byte array. And it kind of makes sense if you look down here, what are we actually doing with A5? Well, A5 is being assigned to, well, here, let's just rename it here. Name arg pointer to byte array. So what are we doing here? We are assigning it to a variable, and then this variable is taking the results from this little XOR encryption routine here. So again, all of this sort of matches up with the pattern that we've already established in our previous video for identifying RC4. And the main thing that made me think that this is RC4 as soon as I saw it was this for loop to 100 hex. And if we look up, just to refresh your memory here, if we look up the RC4 pseudo algorithm, so we have, they initialize a state, which is used for the encryption, and the state is initialized in basically as an array from 0 to 255. So that's 100 hex. And in that array are the bytes, 0, 1, 2, 3, 4, 5, blah, 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 up to 255. So that is actually identical to what we're seeing here. So here we have an array here from 0 to 255, 100 hex, and for each value in the array, they assign it the actual value in that list of integers, so 0, 1, 2, 3, 4, etc. So anytime you sort of see this and encryption, RC4 is what comes to mind. And again, I only know that because I've memorized this pattern, and talk about that again in our video on RC4 encryption, which I will link below. So if you didn't immediately see that, check out the other video, and hopefully that sort of helps you understand how I was able to spot that so quickly. So let's go back and figure out where these arguments come from. We know that this is the output from it, and if we were to go back here, we can see that, let's go back again. We can see that these are numbers. They're most likely going to be the length of the encrypted data and the length of the key, but I don't see a key being passed here. All I see is one blob of data, so one reference to data, which was reference to this block of memory here. So what I'm going to do is I'm going to rename that as a pointer to encrypted data. And so when we come in here, we can name this as a pointer to encrypted data. I'll make it arg. So now we can see something interesting is happening. So the first argument to, we'll just name this malware underscore RC4. So because we already established it's RC4. And I will actually validate that for you guys in a second. Once we figure out these arguments, I'll show you, I just guessed it was RC4 because I saw that loop from 0 to 255. But basically, I'll show you guys how to validate this. So let's take a look at our inputs here. We know that there's a big block of data. We are taking a arg2 is a pointer to somewhere in that data. So we'll call that arg data pointer. And the second argument is just passed in directly. Then the third argument to RC4 is the pointer plus A3. Okay, so I think I see I see what's going on here. So with RC4, obviously you need a data, the length of the data, a key, and the length of a key. So you usually have 4 arguments. We have 4 arguments here. So this, I'm assuming, is probably the key. So this block of data has some offset where we're sending the pointer to point to that offset. That's probably where the key starts. This is most likely the length of the key. Then the encrypted data starts, so here's your key, the encrypted data starts right after the key. So you have the length of the key plus the start of the key, then you have the encrypted data, and this is probably the arg length of encrypted data. All right, and then that's obviously the output from RC4. So now that we know this, we can come back to our function here. So we're going to call that malware decrypt string. And so we know what these arguments are now. We know that the first argument is a pointer to the encrypted data table. Then we have the encrypted data, the offset of the key. Then we have the length of the key. Then we have the length of the encrypted data, and we have the output. And I'll just sort of make these all nice here. Okay, so now we know what all these are. So if we go to our data table here, because this is indexed as offsets, IDA thinks that it's an array, which I mean, I guess it kind of is, but in order to make it easier to view, I'm just going to select it all, and I'm going to undefine it with the U command. So now when we go to it, it's all undefined, and it's going to be easier for us to sort of figure out what's going on here. So if we go to our table here, we go to the offset 7BE. So let's do a little math here. 0x7BE plus 41CC28, 0x41CC28, and we'll make that hex. All right, so this is the offset here. So 41D3E6. So we can just double click on this to get to the address here. 15 bytes. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 bytes. Guess I grabbed too many there. And this is going to be the encrypted data. So I'll just grab a bunch of that. And so we have our 2 strings here, and we can just do a quick RC4 decryption. So I have the RC4 algorithm that I put on my gist in the last video. So I've just grabbed that here. I'll paste it into our command line here, and then I'll do an RC4 decrypt and see what would I get. So the first parameter, the key, is going to be, and the next parameter is going to be the data. All right, so this is the output, and remember it's a wide string. So what we can do is we can grab that string and we can do a replace of the null characters and replace them with nothing. Oops, there we go. So we can see we start to decrypt a string here called global something. And remember, this is a mutex, so it makes a lot of sense that it would be global prefixed with a backslash as that indicates a global mutex. So that makes sense. It looks like we've actually confirmed that this is RC4 encryption, and it looks like we've confirmed that this is in fact the string decryption function. So far so good. And you saw that we could manually decrypt that string using the RC4 Python algorithm that I developed in my last video on RC4, which again you can grab from my gist, and I'll link that below. So that's what I copied in here. Now what we should do is we should do a little xrefs here and see where else we have encrypted strings in the file. So there's quite a few different encrypted strings being used throughout. So you can see there's some here, there's lots of strings here. Now you could go through and you could go to each one of these offsets here. You could go to this data section here, go just like I did before, copy this offset as the key and the data and decrypt it, and you could copy it back into your IDB. But of course, if you look at it, you can see that there are a lot of these strings. And so the better way to do this is to write a small IDA script in order to actually do the work for you. Now, I've sort of cheated a little bit, but I'm going to help you guys cheat as well. So I've already created a few helper functions that work for the ID7 API, and I'm going to paste them into this text editor here so that you guys can see. First, let's make the font a little bit bigger for you guys. So what I've done is I've created some helper functions for the ID7 API that allow you to automatically get all of the xrefs to a function and to automatically pull in all of the stack arguments. So what I'm going to do is I'm going to link them below in a gist so you guys can copy them out, and I'm going to copy them over to this text editor here so you guys can sort of walk through and understand how they work. But what we're going to be doing is we're going to be using those to actually build our string decryption tool. And instead of trying to build them from scratch, I'll just copy them over. I reuse them sort of like a library, basically, in all my scripts. So you guys can do the same thing. So basically, there's a few of them. The first ones here are to set a comment. Let me, if I'll save this out to our desktop here as... Okay, so the first thing is you can basically pass a text string and an address, and this will automatically set a comment in both the disassembly and in the decompiler on the same address. So this is very helpful. For example, once we're decrypting the strings, we're going to want to label those strings in your IDB, and I like to add them as comments. And I like to add them in as comments both in the decompiled view in Hexrays and also in the IDA disassembly view so that I can see them in both. So these helper functions here, you just send set comment and it'll set comment for both the disassembly and the Hexrays view. The next set of helper functions that I have are a little bit more in depth here. They are pretty big. What these do is these will grab all of the stack arguments, and I'm going to show you how this works so you understand what I'm doing here. So let's pull this up in a split screen here. So if we look at this call here to decrypt string, what we want to do in order to decrypt the string automatically is we want to find these first 4 arguments that are passed to that function. And you can see here they're passed on the stack. So they're pushed onto the stack here. There's actually 5 of them. So this is where they return the decrypted string. But we only care about the first 4. So they push on the pointer to the encrypted table of data in the binary. They push on the offset to where the key starts. They push on the length of the key, and they push on the length of the data. So these are just like what we saw in the decompile view here. These are the arguments, and this is how they look when you actually look at the disassembly. So what I did in IDA Python here is we pass it the address of the function, and we walk back. So we do previous head, which means the previous decompiled instruction. So boop, boop, boop. So we walk back. For each previous head, we look for a push, because of course the pushes will be pushed onto the stack. And we look to see if the operand is an immediate. And that means that it's not a register, it means that it's an actual value. So if it's an immediate, then we add the operand to our arguments. And if it's not an immediate, if it's a register, so for example, we don't have an example here. Maybe here would be an example where if it's a register, what we do is we use this second function here and we walk back further from the register to see what was loaded into or moved into the register. So by using this, we can basically just make a call to get stack args, and that'll return the last bunch of arguments. And I'll just show that to you here in IDA. Just copy these out, paste them in here. And so then we can use something like get stack args for this address of this function call here. And we want to get the last 4 arguments. There you go. So it prints out the last 4 arguments, and we can just double check, is that right? Yep, 401CO440, right? And if we go back, 607, B, and 2, right? So we managed to grab these 4 arguments right here. So there you go. And I guess I didn't show you the comment one working either, but I mean, you kind of just trust me that it works. I'll just copy these over into IDA here. So we can do a set comment, and let's say for what address should we set it for? Maybe for this decrypt string address again. And let's say hello. So you can see that it set the comment hello here. You're like, why didn't it set it here? Well, actually, this is a view that needs to be refreshed once you update it. I don't auto refresh in the comment set. That actually might mess some other stuff up if you use it in a script. That's why I don't do it. But you can easily auto refresh this just by kind of popping back and forth, and then you can see the comment here. Hello, it's set. So you can see that those work. And then the final thing that I have to sort of make this go fast is I have a sort of a wrapper around the get xref command. And what this does is there's already an IDA command, xrefs2, that you can use to get all of the cross references to a function. And of course, that's what we're doing when we come in here and we right click and say jump to xrefs. So all of these addresses here where this function is called, that's basically available to us in the IDA API. But what it does is it creates a generator with objects, and each object has a bunch of information about that call. All we want is the address of that call. So I've written a little wrapper script here that will just get you all of the addresses for that function call. And so you can do something like this, get xref list for the for this function here. Forgot to import IDA details. There you go. So all these addresses are the cross references. And if we were to go back here and say show xrefs, it should be pretty much identical, right? So this shows it with the address plus the offset in the function. This actually just computes the full offset in the binary. So, so we have those functions available. So now you can kind of see from those couple functions, you can see the direction we're going. Basically what we want to do is we want to say, give me all of the references to this decrypt string function. So show me everywhere in the binary where that's called. Then for each one of those references, get the previous 4 arguments that are passed to that function. So those would be the data that you need in order to actually decrypt the string. And then we're going to use that to actually pull the string table out of IDA, out of the binary, and decrypt the strings for us. And then we can just add them back as comments for each one of the function calls. So let's pop over here, and I'll copy in my pre-made script so I don't have to type it all out in front of you guys. Here we go. Here's our decrypt string. And the first thing we do is we use that get stack args, as I previously demonstrated. We pass it the address where the function is being called. So that would be this 4151E. And it will return to us the table start, the offset, key length, and the string length, right? Those are the 4 arguments. And then once we have those, I just have this little try except in here. And I'm gonna actually add into our file here, I'll add a little custom exception handler. For those of you who aren't super familiar with Python, all I've done here is I've just defined a custom exception that I get to raise myself anytime I want. And what that does is that will actually allow me to throw exceptions if things are going wrong inside of our decryption here. So for example, if we aren't able to find the arguments, I can throw a decryption error, and then I can handle that later on in the code. So right here, we basically just handle it. If we're not able to get the arguments, we just print we can't get the args. Otherwise, if we do get the arguments, what we need to do is we need to use this IDA function called get bytes. And again, I've talked about this in the previous IDA scripting video, where you can basically copy any data from IDA using the get bytes, as long as you pass it the address where the bytes start, and the length of the data that you want to copy. So of course, like we saw before, it's table start plus the offset to the key is the beginning address, and then you have the key length. And then the data is the key, the end of the key, so that's basically the offset, plus the key length, plus the table start, and then you have the data length, and that gives you the data. And of course, we haven't copied in our RC4 decryption yet, but I'll just go ahead and do that right now. So we have our RC4 decryption algorithm, which I copied from our last video where we talked about RC4. So now that we have all of that in place, we can actually do the RC4 decryption. Here's our plain string. We print that out to the console here so that we can see whether it worked. And we also use set comment to add a comment at the address where the string decryption function is called. So what I'm going to do now is I'm going to recopy all of this stuff into IDA. Just paste in the console window here. And I think I need some imports. I'm going to import a bunch of libraries from IDA. So these are just the IDA API libraries. And then what we can do is we can use this decrypt string function, and we can decrypt string at the address, let's say this address right here. There we go. And so what it's done is it's decrypted it, it's added a comment here. If we, again, this hasn't been updated, so we have to go back forward. So it's added a comment in the hex phrase view, and we've also printed out the string to the console here. We now have a working string decryption function, which you can use to decrypt the strings manually. Now what I want to do is I want to automate it. So I'm going to create a function that basically loops through every reference to this string decrypt function. And then for each one of those, it calls this decrypt string function. So what I can do here is I can basically create something called Decrypt All Strings. And we use our getXref list, like I just demonstrated, to get all the references. And then for each one of those references, we pass it to decrypt string. So let's copy this out into IDA here, and we'll give it a shot and see whether it works. So instead of passing it the address where the function is called, we have to actually pass it the address of the decrypt string function. So I can just double click on it and grab the address here, decrypt all strings. There we go. So I'll make this a little bit bigger so you guys can see it. So we've decrypted all of our strings in the binary, one by one. Printing them all out here with the offsets, and if you jump to the offset here, you can see we've added the comment in hexarrays, and we've added the comment here in the disassembly. And this is actually the reason why this is really helpful to print it out like this, is not only because then we can see all the strings in the binary, but also when you start reverse engineering the binary, once you've got it all cleaned up and all the strings added, it's actually kind of easy to jump to interesting functions. So here we can see the command for VSSadmin. So this is the volume system shadows, which is usually used in ransomware. They usually call this to actually delete the shadows. So you can see delete shadows, which removes Windows backups. So what we can do is we can actually double click on this address here, and we know that this function here is being used to actually delete the backups. So we can see these strings here. I'll actually make this a little bit bigger here so you can see what's going on here. So this function here, which has these two strings that are decrypted, this string is being passed to LP file. This is being passed to the parameters, and then we're calling shell execute W. So this whole function here, you don't even really need to do very much reverse engineering. You can just rename it as malware delete VSS, right? So now that you have you've decrypted the strings, and you've decrypted and you've resolved the dynamic imports, it's actually really easy to reverse engineer this malware. You can start labeling stuff. And again, just like a normal binary without encrypted strings, your jumping off point would be interesting strings here to look at. So you can see here is like a user agent header. So you can pop over to that function and see what they're doing here. Obviously, they're doing some sort of internet connection stuff. So you might want to look at that in terms of like how, if there's like a C2 functionality or something on this malware. So there you go. That is how you decrypt strings in a nutshell. So the first step is to identify, are there encrypted strings? And you do that by identifying API calls that take strings, and then you look to see if the string that's being passed into it is encrypted or not. If it's a plain text string, it exists in the binary. If not, then figure out where the string comes from and try and identify the algorithm that's used to decrypt it. So again, most of the stuff is probably going to be RC4 because it's really simple to implement and a lot of malware uses it. So you should definitely check out our other video on RC4 encryption so you can spot those patterns. Once you have identified the encryption, test it out, make sure you're able to decrypt the strings, and then use our helper functions here that I'll link in the gist below to automate the identification of all the function calls to decrypt string, and grab those arguments and then decrypt the strings and add them back into the binary yourself. So once you've done that, you should be ready to start reverse engineering. And as I demonstrated, once you have all your plain text strings and all of your imports resolved, it's actually quite easy to figure out what's going on in the binary. So hopefully this is helpful to you guys. What I think I'm going to do is I'm going to make a playlist in our YouTube channel called REvil Reverse Engineering, and I will put all the videos in there so you guys can watch them from the beginning to the end. And then this is basically the final stage before you actually start reverse engineering the binary fully. So let us know if you want to keep seeing these deep dive videos, or if you're interested more in seeing some different topics, some of the shorter stuff that we're doing with unpacking. Let me know below. Definitely check out our UnpackMe service. It's working better and better every day. The more samples we collect, the more we're able to unpack. So definitely check that out. And also coming soon, we will have decrypted strings, just like I showed you here, automatically displayed in UnpackMe. So that's a feature that's coming pretty soon. We'll have a little release announcement about that. So that should sort of help speed up your reverse engineering as well. So until next time, keep exposing the mechanics behind the malware. Stay curious.